In this video, I'm going to be going through a trust question from the 2013 trial. I don't know the number of the question, but it's depicted here. Now, I'm teaching this as a three-force method question. I'm not going to do the analytical solution in this video. I'm just going to solve this graphically, so that for students who are learning the three-force method in year 11, this would be relevant to you. So the first thing I need to do is, when I look at these diagrams, I count how many forces are there on this diagram. So there is 1, 2, 3. For year 11s who aren't familiar with reactions, what we have here is we actually have a roller, and rollers always push up out from the direction of that arrow. So we talk about it being a perpendicular reaction, but for your circumstances, you can just replace that with an upwards arrow. The pin, on the other hand, could be any angle. We don't know what that angle is. So I've shown it here as this wavy line. I know that it's because I have this force here going to the left, that actually means that this force is going to be going to the right. This arrow is going to be going actually backwards. So it's going to be like that, after all. But that's why I can sort of say intuitively it's probably going to have to go something like that. So let's see. We've got three forces. We've got two reactions and one external force. If you see a truss question that has two reactions and one external force, you should think three-force rule. Now the next thing you should look at is say, well, three forces in equilibrium must either be parallel or concurrent. They can't be a mixture. They have to be all parallel or all be concurrent. So if we have a look here, well, we can see this here is an unknown, but if we look at the two forces we do know, we can see, well, are they parallel or are they not parallel? Do they meet? There's some way that they meet. And if there's some way they meet, that means they're not parallel. So let's find that place where they do meet, what we call the point of concurrency. So what I'm going to do is I'm going to extend this line. Did I actually draw that at 60 degrees? I meant to, but anything's actually a little low. It'll do. I'm sorry, I'm going to extend this one here up. There we go. Now, I'm going to call that my point of concurrency. So, red lines, we find the point of concurrency. We find where these 2 points meet. Once we've found the point of concurrency, the next thing we need to do is we need to find the angle of our unknown force. So this here, this RR is what I've got written there. What we need to do is we need to find its angle. So what we do is we say, well, obviously the angle of RR passes through this point, and also has to also pass through the point of concurrency. So it's going to look like that. It's going to be that angle. And then I can get my protractor out and I can measure that angle and I can say, oh, that's 56 degrees. Now, you notice I'm calling it 56 degrees. I've measured it from a drawing I did on the paper, which I'll show you in a second. But that's 56 degrees. Doing the same thing on a piece of paper. So once I've identified that the three-force rule applies, the first step is I draw these red lines. Then I find the point of concurrency. Then the next step is I draw the green line that goes to the point of concurrency to find this unknown angle. Once I have the unknown angle, I can then use the sine rule, or I can solve it graphically. If that's 56 degrees, it means we now know the angle of RR, that it's going to be 56 degrees. Now, the next thing we need to look at is, well, what we need to do is we need to take these three forces. The last step of the solving things using the using the three-force method is we could then solve this thing either using the sine rule or using a graphical solution. So I'm going to first try and solve it using just measuring it out with a protractor, and then after I measure with a protractor, we're going to solve it using the sine rule. So what I have here is I have this force here is going to go just like this red arrow where it meets. If I draw that exactly, it's going to be 100. So it's hard for me to get the protractor up there. That'll do. Close enough. Okay. So I've said this one here is going up. That's RL. This one here's going down. It's going to be 100 kilonewtons. And then we need another force, which is going to be going in this direction, which is going to be 56. Now the question is, when we draw these, is how do we know where to start that last line? This last line that's going to be going, it's obviously going to have to be going down this way. It's 56 degrees. But where does it go? Where do I put it in that diagram? Well, what we're going to do is we're going to take the one side that we do know, which is the 100 kilonewtons. We're going to take the 100 kilonewtons and we're going to measure this to our scale. Now, I've decided to make it nice and easy to see that I'm going to say my scale is going to be 200 millimeters equals 100 kilonewtons. Yeah? My thing is twice as big as it should be, which means my scale is twice as big as it should be. It's the same as writing 2 over 1. Yeah? 2 over 1. My scale is twice as big. Okay, so now that I have that, what am I going to do next? Well, I've now drawn the dot. Now what I need to do is I need to draw this line here at 56 degrees. So to make sure that I'm getting my angles correct, I'm going to draw a little green line just to make sure that that's my horizontal. And now that I have my horizontal, I'm going to draw that all the way out, actually, because I have a very big protractor. There's an office joke in that, I'm sure. And then from the horizontal, I'm setting my protractor to 56 degrees, which is what I measured earlier. 56? Oh, that's actually 58. It was 58. I just wrote a terrible 6. 58. Good work checking. So I'm setting this to 58. And then, what I'm going to do is I'm going to extend this line down to where it meets, where these cross over. And where they cross over is going to be the actual values. So we said RR is going to, remember we predicted right at the beginning that RR is pulling down on this truss. We predicted that earlier. I drew the wavy thing, I then changed the head of the arrow to say, well, if this is going to the left, we need something going to the right to keep it balanced. So this is going to have to be going to the right. But if we look now, we can see that our vector diagram is going in an anti-clockwise. All the arrows are going in the same direction. They're all going anti-clockwise. So remember, when we add vectors, that if the vectors are in equilibrium, that means the resultant or the missing force, the leftover force, is 0. Yeah? If something's in equilibrium, it means there's no resultant. It means if you add vector A, B, and C, they end up back where they start. It's like if you go on the marathon and you start at the Sydney Harbour Bridge and you end at the Sydney Harbour Bridge, your resultant is 0. This runner has started at Sydney Harbour Bridge, they've run, and they're now back at the Sydney Harbour Bridge. Their resultant is 0. So it's in equilibrium. If it's in equilibrium, the resultant is 0. So that means these three forces together add up to where they start. If we look at the start and finish, they're the same place. Okay, so looking at this, because I know this angle is given, I'm going to write this in purple just to show that this first angle here was given as 60 degrees, and that this angle here is 58. I can say with a fair degree of confidence that this number is going to be pretty similar to that number. Yeah? Because the angles are so similar, this number is going to be very, very close. But we'll measure it out and we'll see what answer we get. So what I get here is I get 185 millimeters. 185 millimeters. And so when I divide that, what do I get? Just for the sake of simplicity, we're going to call it 186 millimeters, right? I'm going to round up. How many, if I divide that by 2 to get our scale, what force am I going to have?
93.
93 times 2 gives us 168. So this is kilonewtons, and that's because this is millimeters at our scale. So we've now found our reaction RR. I'm going to write that in black because that's my answer. 93 kilonewtons. And then we have this value here, RL. Let's measure it. $325. 326 millimeters. So we're going to have 150 plus 13, which is 163 kilonewtons. Yeah. Excellent. Thank you for looking that up. No one wants to be wrong on the internet. Okay. So that's the answer I could give. I could say RL equals 163 kilonewtons and 93 and RR equals 93 kilonewtons. Let's see if we can get a slightly more accurate answer using this value that we've measured. Right? We still are using a value that we've measured, so it's still a partially graphical solution. But now that we know this value, what we can do is we can solve this same triangle. We can solve it graphically. So what I'm going to look at here is I'm going to say, well, this is my diagram. It looks something like that. I'm told that this is 100. And I'm trying to find these other sides. Okay, so we know that this is 58. So if this is 58, what is the inside value of this angle here? 58, what's this value here? It adds up to 90 degrees. So if it adds up to 90 degrees, what's the value? 32. 32, sounds exactly right, yeah. Okay, this angle here, what's it going to be? It's going to be 60 plus 58. 60 plus 60 is 120, so it's going to be?
180.
Excellent, thank you. Okay, and then lastly, what's this value going to be? Well, if I was smarter, I could do this in my head. I could say that's 120, 150, it's probably 30 degrees. How do we feel about that? Where did that number come from? The angle sum of a triangle has to equal what?
180.
Yeah. So that means this plus whatever this is has to equal 180. So you guys will type that in and check that for me. Now, we've got names for these other sides that we're trying to find. We're calling this one here RL. We're calling this one here RR.
So it's 40.
40? Ah! Excellent. Look at me not using a calculator, trying to show people I'm smart. Hopefully you guys all had that sentence, you know, those viewers at home said, that Luke, he wasn't wrong on the internet, he was just checking to see if people... Anyway. Okay, so what we know is, we know that this angle is opposite the 100. The 100 is given, right? So we want to find the angle that is opposite. So the sine rule says A over sine A equals B over sine B. Do I need to write that? I hate writing that. A over sine A equals B over sine B.
So
now, yeah?
I'm pretty sure it is 30.
Yeah, I got the...
Wait, what?
180. I might have got 172.
Ah, that Luke wasn't wrong. He was just checking to see if you're paying attention. I tell you why I was pretty confident it was 30 until someone told me otherwise. Is because if I look at this triangle here...
No, it's 18 plus 30.
Look, this one here has to be 30. Right, I'm now confident. I'm now locking it in. I'm now willing to be wrong on the internet and say I think that one's 30. Yeah, but thank you for.
Oh, it's 180.
Yeah. Okay. Hey, look. You know these questions are important. I don't think I'm going to edit that out. I think I'm going to leave that in. So this is the sine rule. But what we're going to do is we're going to replace sine A with our unknown. Which one are we interested in finding first? RL or RR? RL. Okay, we're going to find RL. So RL is here, and its opposite angle is there. So RL is an unknown, so we want to write the unknowns on top. RL over sine 118 equals this is our known, so 100, and the opposite angle is 32, sine 32. We can then multiply both sides by sine 118. What happens there is this then cancels out. So what we can rewrite that as RL equals 100 sine 118 divided by sine 32 equals 100 sine 118 divided by no, I know I have to type in the whole thing on my calculator. I have to type it in one line at a time. Equals that divided by sine 32 equals that. I get an answer of 116. Sorry, 166. 166 rounding up to 167 kilonewtons. Let's have a look. How does that compare? That's pretty close. So our actual answer, we're going to go 167 kilonewtons. Right? And then, if we do RR, using that same method, we can say that RR equals 100 sine. Now, what's the angle that corresponds with RR? 30 divided by sine 32. I'm just going to remove that line because I don't think that makes life easier. Okay. 100 sine 30 equals 50. Sine 32 equals 94. And that's 1 Newton off. So, that's our two methods. Let's go through again what the process was. The first process was we looked at this and we said, how many forces are there on this truss? In this case, there was 2 reactions and 1 external force. That gives us 3 forces. We've been told that we were able to look, we didn't know this at value, we didn't know this reaction. We didn't know that reaction. So we looked at these two and said, do they meet? If they're parallel, don't worry about it. But if they are parallel, that means, if they're not parallel, that means they meet at a point of concurrency, which I've shown here. Then, once we've drawn our red lines to find the point of concurrency, we can find our green line to get our green angle. Once we have our green angle, we can then solve our question using our green angle here, and we can either draw a diagram to scale with a protractor and a ruler, or we can use a mathematical solution using the sine rule. I don't care which of these two you use. The sine rule will probably be slightly more accurate, and if you're more comfortable with that, that's a really good approach. There's nothing wrong with finding the angle, and once you've found the angle, then using the sine rule. But it's way faster than the mathematical solution that we'd use if we didn't find that point of concurrency. Now, maybe in another video I might solve this without using the point of concurrency or provide answers without using the point of concurrency. But for year 11s who are still doing chapter 2 of the preliminary course, this is pretty much the way that we're going to solve it. So that's the 3-force rule as it applies to a past HSC question.